Good morning. So I wanted to, since I think it was not clear which derivatives were discontinuous, which derivatives were continuous in this phase transition that I described last lecture. So I decided to go back and show you explicitly what happens. From nothing new. It's just that that I want you to see explicitly the function. So this function G is the free energy at constant pressure that you find in the. By the way, this is taken by Kittel's book, which is called Thermal Physics. But we are not even following its notation. So G in those notes, in those copies, is our Gibbs free energy phi, which is the thermodynamic potential at constant pressure and temperature. Okay. So the question is the following. So you see, for example, if you look at the second graph. Free energy, some dimensionless quantity, so it divides by the number of particles times Tc. This will be Kb Tc. Okay, so this is dimensionless because the free energy is an energy and Kb Tc is an energy. And n is because the free energy is extensive, so we want something which is of order 1, not of order 10 to the 20. Okay. So if you look at this graph, this looks something like this. Okay? As a function, this is at constant temperature. Okay? As a function of the rescaled pressure. This point here is slightly larger than 0.8. I would say it's something around 0.81. Do you agree? Look at the graph. Okay. Very good. So this is the liquid branch. This is the gas. So pure liquid and pure gas. And what are these other things here? Well, this is the analytic continuation of the free energy of the liquid as a function of the pressure. And this is the analytic continuation of the free energy of the gas at constant temperature as a function of the pressure. And this here is a completely unstable branch. Now we'll see what it means. Okay. So, as you see, we always have to take the minimum of the free energy. So we have to completely forget about what's above this curve, and the real curve that we have to look at is this one, not the dashed one, the continuous one. Okay, as you see, this curve has a discontinuity, is continuous. Okay, because I can draw it without taking out the pen from the paper. But its first derivative is discontinuous, because the first derivative here. It's like this, and here it's like this. Okay? So now, I know the van der Waals isothermal looks. This is an isothermal process. So I just need to draw one of the isothermal curves. This, for example. That corresponds to T equal to 0.95 Tc. So, I come down from high pressure, for example. So in this graph, I am where? Speak up. Upper left here, okay? So this is all liquid. And then I go down And I know that there has to be a Maxwell construction. Then the pressure has a certain value, and if I lower the pressure, then I go in the gas phase. Okay. What are these other points here? So first of all, what is this point here? It's the Maxwell construction intersection, right? So let's call this point A. So this point will be here. But you see, if I lower the pressure before I get there, something happens. Where in this graph?
The decreasing part.
The decreasing part, this one?
Yeah.
No, I'm a higher pressure than the Maxwell construction.
Oh, yeah, okay.
So I'm here, right? Higher pressure. So where is this point? Is this point here? So when I lower the pressure, what is the trick, right? We have the free energy, which is a function of temperature, pressure, and the volume, right? And we have to find d phi. Actually, the free energy is a function only of temperature and pressure. Why? Because if I have a free energy as a function of the volume, I have to find the volume by minimizing the free energy. Okay? But this solution is equivalent, as we say, this equation is equivalent to the van der Waals equation of state. But van der Waals equation of state looks like this. So if we want to find the volume that gives a given pressure, below a certain pressure, there are three solutions. This, and this, if the temperature is below the critical temperature. These three solutions, we get these three solutions, as I said, and we have to find the free energy of these solutions. Okay? And then we have to look for the lowest free energy and use the solution corresponding to the lowest free energy. Is it clear? It's very simple. I mean, I'm sorry, I'm repeating over and over. It's very simple. You have a function which has three stationary points. One of them is a maximum and two of them are a minimum. We have to look for the minima, and we have to look for the minimum that has the lowest overall free energy. In fact, this branch here, so if we are at constant pressure and constant temperature, we have, when we are below this pressure here will be the point B here. It's not the critical pressure. The critical pressure is way up. It's here. When the curve starts becoming, starts having a non-monotonic behavior. This is the critical pressure. This is below the critical pressure. So critical pressure, you see, this is something like 0.85. The critical pressure is here, 1. Okay. So below this point, there are three solutions. One corresponds to a maximum, and it's this one. And two correspond to a minimum, this one and this one. Before the Maxwell construction sets in, this point here wins, so has the lower free energy overall. So here, we have to get this point. This point is the stable phase. Okay? This one corresponds to a local maximum, and this corresponds to a local minimum. but not global minimum. But then when we lower, we keep lowering, okay? I can keep asking forever. So if we keep lowering the pressure, then at a certain point there is Maxwell construction. But Maxwell construction on this point here is not really a construction. It's just the point in which these two curves exchange. So this is a local minimum and this is a local minimum, but it's also a global minimum and global minimum. At this point, this local minimum becomes the global minimum. And this local minimum remains just a local minimum and loses the global property. Okay? So we go up here. Then we keep lowering the pressure. And at a certain point, there are always three solutions to the equation. So there are three possibilities for the stationary points. And at a certain point, these three possibilities disappear in the point C here. And only one solution remains. And so we have only one. Okay? Speak up.
Didn't we remove that part because it is not physical? Or
The question, which part?
by Maxwell construction, where we considering it again?
So we did not remove the points here. Okay, we did not remove the points. They are there in the curve. It's just that the system will be in unstable equilibrium on this branch, supersaturated liquid or supersaturated gas here, okay? And these are the local minima. And and the system gets perturbed, so in most of the situation, you don't have a clean system. So you never see this thing here. But if you do an experiment, you can see it. Okay? Then this gets substituted by Maxwell construction, which means that the system phase separates. There is a part of the system which is liquid and a part of the system which is gas. Okay? We have not removed it because they were unphysical. The local maximum, this part here, this is another story. This is like trying to keeping a pencil in equilibrium like this. Any arbitrarily small perturbation will make it fall, because it is a stationary point. There is an equilibrium of forces. If you put perfectly a pencil standing on its tip, if you put it exactly at 0 degrees, there is equilibrium of forces, right? Because the gravitational force will pull down like this, and then the reaction force from the table on the tip will pull like this. So there is equilibrium of forces, but this equilibrium is unstable. It means that anything that comes and hit the pen will make it tip. This is a local maximum of the potential. And so even though the sum of the forces is equal to 0, the equilibrium is not stable. It's unstable equilibrium. And this corresponds to this branch here. So this is really the unphysical part, in the same sense in which the equilibrium of a pen on its tip is just a mathematical construction. Okay, but it's there in some sense, it's there as analytic continuation of the other. Because you cannot have a continuous function which has two consecutive minima without having a maximum in between. Right? Minima and local minima, local maxima for continuous function always alternate. So that's why in Maxwell construction we considered, when we did the integral, we have to consider this part too. So it means that there is information in this branch here. It's not that it's completely out. But it's not possible to put the system in this. Although it's possible, if you are very careful, to put the system here, it's impossible to put the system here. So, okay, so let me repeat. It's not that this part here is unphysical. It's just that in common situations, you will have the phase separation of your system. Okay? And so the Maxwell construction is what you should do in thermodynamics. But if you're particularly careful, you can prepare your system either here or here. But keep in mind that if you wait enough, any arbitrarily small perturbation, like, I don't know, a car passes by and your system vibrates a little bit, then the system will go to the Maxwell construction. By the way, Maxwell construction, the entire line here is just a point, because you don't have the volume here. Again, if you had the volume, then this thing will split in a third dimension. So for given temperature and given pressure, there is only one point. So do you see the origin of the discontinuity in the derivative? It's because above this pressure, we have to take the free energy, the value of the free energy in this solution, and below this pressure, we have to take the value of the free energy in this solution. So the two values are equal exactly at the point A, but they behave like two different functions. So they have first derivative, which is different. By the way, I wanted to mend something that I most probably did last lecture and also the lecture before, which is, I call this thing enthalpy. This is not, sorry, this is not the enthalpy. Sorry, you should have corrected me before. The enthalpy is this free energy at constant pressure and volume is E minus Ts plus PV. The enthalpy does not have this part here. Anyway, there are so many thermodynamic potentials that I think they're, for a physicist, they're a heritage of the engineers working on these things. But actually, in practice, in physics, we never encounter anything which is not either this free energy, which is called Gibbs free energy, or the free energy E minus Ts, which is called Helmholtz free energy. But they are both free energies. Never use the word enthalpy in my works. So, okay, so this is just a function of the pressure for constant temperature. We can do the exercise of doing the same thing as a function for constant pressure as a function of the temperature, and see whether the derivative. So this tells us that the derivative of phi with respect to the pressure is discontinuous at P. By the way, this is 0.81, okay? It's continuous at P equal P star, which is a function of the temperature. So last time, do you remember when we did this construction approximating the van der Waals isothermal close to the critical point? We had an explicit expression for where this P should be. Do you remember? Where was it? Where Maxwell construction set in. It linked the pressure and the temperature. Yes, dP was equal to 4 dt. Okay, so this was correct up to order dt square. Okay, so here, what is dt? What? No, d. 1, so 0.05? Positive? What is dt? It's t minus tc, right? Divided by tc. So it's negative. So it's minus 0.05 in this particular example. So dP should be equal to 4 times minus, which is minus 0.2. So the prediction of that approximate form that we had was that dP is minus 0.2. Is it a good prediction or a bad prediction? What does, in this graph, what is dP equal minus 0.2? On this graph, look, I put some numbers on this graph. Where should I? 0 point? 1 minus? Where should I, where is 0 point, this dP equal minus 0.2, where should I put it? Should I put it here? Should I put it here? Should I put it here? In between 1 and 0.8? And what is a little less than 1? No, a number. I want a number.
Before 0.81.
But which number?
0.80.
0.80, okay? So slightly before, let's say here. So it's a good approximation. You see, I mean, this graph here was actually obtained by really finding the real minimum of the van der Waals, the full equation, not the cubic approximation that we used. So you see, we made with this simple prediction, we made a mistake of 1%. I think it's because it's the difference is no, we make between 80 and 81. We make a mistake, yes, of 1 divided by 80, which is 1.2%.
Here, when we plot the Gibbs free energy versus P over PC, there we have, I mean, between, okay, the answer is the line, the curve, which goes from C to B.
Mm-hmm.
Here we didn't see, I mean, we put it as if the free energy is like a single point.
Where is the, no, we put, on this graph, there is this curve here. There are the values of the free energy there. Where is it?
Yeah, we extend analytical maybe, yeah, the line, okay, we extend the line which goes, okay, in the gas state to A, and then we go to B, and then from the liquid we go to C, and then the line BC, but
No, I put in the graph, I put the value of the free energy corresponding to this branch.
yeah, but
It's here. Where is it? It's not a single value. It's a
line
curve.
BC.
It's the line BC. It's this thing here, the local maximum. Okay?
Yeah, but okay.
here. There is a local maximum, and then you see it's the same thing here. So okay. So the point A is here, and then there is this AB branch, which corresponds to this branch here, AB, because as I said, a point A here is a continuous line there. The point, the line AC is this line here, AC.
The point A is, I think, at the middle, right?
The point A are all the middle line. So there is a crossing between this BC here and here, and the A line here, but it's over here. It doesn't make any sense. It doesn't have any particular meaning. I mean, the Maxwell line does not exist here. That's the point. Okay.
Possible to bypass the curve BC just to go from liquid to A and then G.
Liquid to A and then gas. Yeah, that's exactly what happens. You go from liquid to A and then gas. This is what happens in practice. But in order to do all the construction and know where A is, you have to know all the curve, because otherwise you don't know. Okay, let's do the construction. I have to wait for a second. So. Okay, so the free energy now as a function of the temperature. So now I need more isotherms. They all curve down here. For large volumes, they all become ideal gases. So let's take a temperature below the critical temperature. Let's say this is the critical temperature. Let's take a constant pressure below the critical pressure. Let's take P again equal to 0.95 PC. And we have to see what happens when we change the temperature. Okay, we change the temperature here until we find, so when we change the temperature at constant pressure, we cross with several isotherms, because every isotherm is a single temperature. Until we reach the isotherm for which Maxwell construction exists at that temperature, right? And then we pass it, and then we enter in the liquid phase. So if we increase the temperature, let's go the opposite direction. We should find something like this. Okay, and if you look at the graph, it says that this is something like 0.987. It's 7, 2, or 3. 3. I don't know. Let's put 3. So, at constant pressure, again, at constant pressure, as a function of the temperature, there is again a region in which there are 3 solutions. Okay, 3 points that intersect constant a given pressure and a given temperature. Okay. And the first time this happens, you put there is a this is the liquid gas phase. There is a local minimum and a local maximum that are born, and then again you move up in temperature at constant pressure, and then at a certain point you find that one of the new minimum that was born, so this is the local maximum, the new minimum, which was a local minimum, becomes a global minimum. Okay, and then they exchange. Okay, now they exchange stability, and if you go and you keep increasing the temperature at constant pressure, you pass the region where there is no there is no phase coexistence anymore, and everything is gas. Okay, because a point here is completely gas. And you can do the same construction as we did before and find where are the points. Where is this point? Where is this other point? Where is the exchange of stability? And so on and so forth. And also here, look at the number. So we say that dP is equal to 4 dt, right? So we can write this as dP as over 4 is equal to dt. So this time is minus 0.05 divided by 4, which is minus 0.0125. And so dt is 0.0125, so T over Tc is 1 minus 0.0125, which is 0.9875. So it's very close. Okay? Now, if your pressure is 1, so what happens if you increase your pressure or the pressure of your constant pressure line? Then this construction, this triangle here shrinks, because the two minima, the local minimum, where the local minimum and the local minimum and local maximum are born, and when they die, they come close together. And we saw that they come close together like the square root of T minus Tc. So this thing shrinks, and at a certain point, it goes to a point, and instead of having a derivative, a discontinuity in the derivative becomes continuous, but the second derivative is discontinuous. So at P equal to Pc, this point is t equal to tc. And here, the triangle shrunk to a point, and the discontinuity is not in the first derivative, but in the second derivative. And so we have a second-order phase transition. Okay? And so again, we have a first order line that ends into a second order point. Okay, now I really have to change topic, which I should have done 2 lectures ago. But if you have understood the difference between the first order and second order phase transition, I'm happy, because this is a very important concept and comes out all the time. Okay. So we will see in statistical mechanics other examples of these phase transitions, first order and second order, like in ferromagnetic systems, for example, where one can do some actually write down a microscopic model that one can solve. And the phenomenology is exactly the same. Okay, when there is a first order transition, there are 2 local minima which exchange the property of being a global minimum. When there is a second order phase transition, instead we have a smoother change. We don't have this phenomenon of 2 local minima. We just have a smoother change, but still we have discontinuity in the second derivative. Okay. So do you have questions? Let me remind you that tomorrow we have the test. Okay, so we have. Did you study during this weekend, because your other exam was Saturday, right? No?
No, the exam was just for us, me and
Only 2 people. Okay. All right. So did you guys study? Okay. So I want to introduce the concept of chemical potential. And the idea is the following. So we want to study what happens if we allow the number of particles to change in our system. Okay, you can have an external reservoir from where you can take particles, so you can put particles in, or you can study, divide your system approximately into regions where the density is assumed to be constant. Okay, and this is one of the examples that I think the only examples we'll do, since the time is not on our side. So, for example, suppose you have an external source which keeps the system at constant temperature, And the system is composed of two separate containers which have different volumes, okay, but the same temperature. And you allow, and you have a little valve here that you can play with. And you can allow your particles to flow from one place to the other. So if I let my system, for example, put some particles from the first container into the second container, am I doing any work? Yes? Which kind of work?
Like a difference in the number of
work?
I mean, okay.
Can I lift a weight with this? Am I lifting some weight? Am I pulling some strings? The volume is constant, so there is no work. That's the only work we know for gases. So there is no volume change, so there is no work done. Okay? So and the temperature is also constant. So what should we maximize? Minimize, sorry. Which function? The entropy?
Okay, to keep at equilibrium or?
No, I mean, if I want to see in which direction this thing is going and this reaction is going, it's not a reaction, it's the free energy. The Helmholtz free energy, not the Gibbs free energy. Because the Helmholtz free energy is the one at constant pressure. We have to look at the constant volume and temperature. Okay, so dF decreases until it cannot do it anymore. Okay, so you keep exchanging particles. So N1 goes, for example, to N1 minus delta N, and N2 goes to N2 plus delta N, until such that in a way that the free energy decreases until the free energy does not change anymore. And this is the equilibrium condition. Okay? So the free energy of these two systems is, these two systems are not interacting. So if the free energy of the system 1 is F1 and that of system 2 is F2, the free energy of the total system is the sum. F1 plus F2. So, what? Yes. That's why we just sum them. The free energy of the entire system is the sum of the two free energies. Like if I have something which has energy 1 joule and something else which has energy 2 joules, and consider the system as a whole and there is no interaction, then the total energy of the system is 3 joules. So this delta dF is equal to 0 means that dF1 by dN1 times dN1, which is minus delta N, plus dF2 by dN2 times plus dN is equal to 0. And so we have equalities of the free energies derivative. So if I allow for particle exchange between the two systems, subsystems I should call them, then they go to a situation in which the derivatives of the free energy with respect to the particle numbers are the same. These things are called chemical potential. Okay? Yeah.
So, by definition, what
Yes.
is chemical potential?
It's this, by definition. This is the definition of chemical potential. So chemical potential is, by definition, the derivative of the free energy with respect to the number of particles. It's the energy, the free energy change of your system at constant volume, constant temperature, when you add some new particles to the system. Okay? So, for example, is the energy gain if it is negative, or the energy cost if it is positive, of adding some particles to your system without doing any work, without having your temperature change. Okay? It's by definition. Now, for example, for an ideal gas, this is true for every system, okay? U minus Ts, E minus Ts, I don't remember how we call the internal energy. We know what U is. What is U for an ideal gas? Monoatomic ideal gas. 3/2 CV times T, or RT. But here, now let's be a little bit more careful, because we always talk about 1 mole. But here we are changing the number of particles. So it's better if we put explicitly the number of particles in the thing. Don't make this mistake, okay? When you solve problems, if you're changing the number of particles, you are not allowed to use the equation state for 1 mole. You have to put the N in the right places. And here the right place is N kBT. Entropy is 3/2 N kB log T plus N kB log V plus a constant. We can actually see so we have given the expression for a constant, for the constant in terms of when we talked about the Sackur-Tetrode equation, right? But here it's a little bit important, because usually what we look at is the change in temperatures, change in volumes, and this constant does not depend either on the volume or on the temperature. But if you go and look back at the expression of this constant depends on the number of particles. Okay, and in fact you have something that I did not want to talk about, which is Gibbs paradox. If you have 2 gases and you remove the 2 different mixtures and you remove the lid, you let the mixtures mix, then you have problems with entropy counting, which is only resolved if you actually assume that this constant depends on the number of particles. So for the moment, I am keeping it as a constant which depends on the number of particles, and then we'll see, we can argue. Okay, so in this expression, therefore, if I want the chemical potential, what should I do? I should put together U and Ts minus Ts and then differentiate with respect to N. So the differential of these terms are very easy because it's linear in N. And then I'm left with the differential of the constant. So this is 3/2 kBT minus kBT logarithm of, let me put it this way, 3/2 V, and then I have and then I have minus kBt dc0 by dn. So right. Okay. The chemical potential is the derivative of free energy with respect to the number of particles. So do you expect it to be an intensive quantity or an extensive quantity? Extensive? Intensive. We have a phase separation in our... What's an extensive part? What is an extensive variable or function? Just a second. Yes, what does it mean?
We can have, if you have two,
Uh-huh.
you can have
Or if I have one and I double the size or the number of particles of the system, my function does what?
some of
It's the sum. So if I double and multiply by 2, becomes... So give me an example of such a... The volume, for example. Or... Okay, I mean, something we're talking about here. The number of particles, for example. A less trivial example. The free energy, Gibbs free energy, or the internal energy. Okay. And if I take derivative of an extensive variable by an extensive variable, do I expect an extensive variable or function? Or yes? No. If I take ratios of extensive variables, it's an intensive variable. Because the numerator doubles, the denominator doubles, and the 2 cancel out. Right? Derivatives of extensive variables with respect to extensive variables are intensive. Try for yourself. If you multiply the numerator by 2 and the denominator by 2, the 2 cancel. Okay? So mu should be an intensive variable. It's the free energy per number of particles. So, but there is something, okay, this is an intensive variable because it's proportional to the temperature. This is intensive, but this is strange. This is like the logarithm in the entropy. That's why I didn't want to agree with, you said, you mentioned the entropy is extensive. The entropy should be extensive, you're right. But in order for the entropy to be extensive, this thing really has to depend on the number of particles, right? Because this is intensive. A logarithm of an intensive variable. This is a logarithm of an extensive variable, so it's a strange thing. Okay. But if this contains, for example, sorry, there is n. Let's take the n outside. So this is intensive, but this is neither intensive nor extensive. So it means that this thing here should contain something like n kb logarithm of 1 over n times some constant, because it has to get into the logarithm here. Okay? By the way, n log n is the logarithm of which function? More or less. It's not exactly, but n is large. Of n factorial. And in fact, this thing here is logarithm of 1 over n factorial, which is important. It's the correct counting in order to count the different states that correspond, because you can permute the particles. I don't want to talk about this today, because we'll see it in the second part of the class. You will see it in the second part of the class. But n factorial should be there because you can, these are identical particles. So you can exchange them, and they give the same. Anyway, so the important thing is that this thing should actually be logarithm of something on which we cannot say anything, and in fact it contains h bar and blah blah blah, but then it has to be divided by n. Okay, so all in all, we can write this as minus kbt logarithm of t to the 3 half v over n times some other constant. Let me call it alpha prime. I can absorb this 3 half here in the constant. Let me write it like this. Logarithm of the density divided by the quantum density, which is a density which can be built. The density is n over v. And this density here is a density that you can build with the temperature, h bar, and maybe the mass of the particles. Actually, you have to use the mass of the particles, otherwise you cannot build the dimension of a length or of a volume. Okay. I mean, so the value of C0 is that dC0 by dn is equal to logarithm of alpha divided by n. So you do the integration, you see. Okay, so we don't know what this density here is, but it's actually not very important. So let's do an example. Let's have an example of okay, if you're not happy with this ad hoc insertion of this formula here, then you have to wait until the second part of the class where we will actually derive this thing. Okay, so for now, the only thing that counts is the result. For the ideal gas, the definition is true in general. Let's consider Earth's atmosphere. Okay? Up to, I don't know, like 4 kilometers. So if you go on the Mont Blanc or close here, there are many places. There are some places that go above 4 kilometers in height. Or you can take a plane, and you can go up to, I don't remember, 30,000 feet is 10 kilometers, something like that. That's usually when you go intercontinental flights, they go up to 10 kilometers. Okay, so let's neglect the curvature of the Earth. So what's the state of equilibrium of air in the atmosphere? Well, there's a temperature. Okay, we assume that the temperature is constant. It's not a great assumption, but it's okay. Typically, when you go up to a certain value, up to a certain height, the temperature goes down. Then you know, many things happen. So it starts going up again and down, blah blah blah. So let's assume the temperature is constant. And but the energy of the gas is not just a thermal part. Let's assume, for example, nitrogen. Okay, nitrogen makes 78% or 80% of the whole mass of the of air. Okay. So, well, okay, let me put it CVT because it depends when you consider the molecule, blah, blah, blah. So I don't want to talk about the structure. Eh? What I want to talk about is this thing. The potential energy of a particle of air, of nitrogen. So let's assume, for example, let's make this assumption. We can slice the atmosphere in slices of delta H, which are sufficiently big such that we can apply thermodynamics, but they are sufficiently small with respect to 4 kilometers. For example, I don't know, like 10 meters. Okay? And we can, and these things actually, these several slices can exchange particles because particles can go up and down. I mean, this is an ideal line. There is no real line at 10 meters in the air. Okay? This is an ideal line, so particles can go up and down. They don't do any work. Okay? Because they just move up and down. There's no change in volume, no anything. So the change in the chemical potential between different slices, if we are at equilibrium, is equal to chemical potential is 0, right? The change in chemical potential is 0 because that's the equilibrium condition. So I can divide it by delta H and I get 0. The chemical potential is the derivative, as we said, of the free energy. And the free energy contains now also these terms. So the chemical potential of an ideal gas in the gravitational potential is not just the term that comes from this thing. The entropy is not changed. The entropy is always the same. It's not influenced by the external potential. So this thing will be the thing we have calculated before, which is kBT log of rho divided by rho Q. But now rho depends on H. It's the density. Okay? And we have an extra term, which is the derivative of the new part of the derivative of the free energy with respect to the number of particles. So it's just mgh. Okay. So the derivative. So if I now translate this into differentials, the derivative of a function being 0 means that the function is a constant. Okay? And therefore, we can solve this equation for rho of h. Rho of h is equal to okay, so this has to be, to be equal to It's not equal to 0, but equal to mu of 0. Okay, it's a constant. You don't change h. This is much better because instead of now, if we take the differences, instead, this is 0, but here instead of having rho of h, we have rho of 0, and we have rho q. So this thing becomes rho of 0 e to the minus mgh divided by kbt. You see how many times we solve differential equation in thermodynamics and something like e to the minus something divided by kbt occurs. Okay? Now, what does this mean in terms of measurable quantities? The change in density at given temperature, at fixed temperature, which physical property influences that we can measure very easily? The density? Okay, and this we got it. Okay, so we have the density consistent with the height, but something we can measure. We don't measure the density of air usually, right? But we measure the pressure. So what should I use? Manometer, very good. Okay, which equation should I use? To link the density and the pressure. P is equal to, so PV is equal to N kBT, right? Okay, so P is equal to rho kBT. So if I multiply the two sides of this equation by kBT, I get that the pressure F at height h is equal to the pressure at height 0 times e to the minus mgh divided by kBT. So in principle, if the temperature were perfectly constant, by measuring the difference of pressures between different heights, I could get the mass of nitrogen. So actually, let's.
Can you use Clapeyron to find the pressure?
Clausius-Caperion is used for what? What is the equation?
dp by
What is the equation? What is Clausius-Caperion equation? But dt is equal to
is equal to the latent
heat
vaporization
of vaporization
over the product of between T and the change in volume.
So where is the vaporization here? That's used to study phase transitions, right? Phase coexistence, actually. So here we don't have any. Okay. So this I leave to you as an exercise. What is the pressure at 4 kilometers? Assuming the temperature is equal to, let me use the same numbers that I used. 290 Kelvin, and assuming that the pressure at 0 is equal to 1 atmosphere for nitrogen. Nitrogen molecules, okay? If you want extra points, you can use Clausius-Caperion equation to calculate what's the change in the boiling temperature of water at this pressure here. Okay? The boiling temperature. Because the boiling temperature depends on the pressure. They are linked. There is a line. And so you can see why coffee and pasta are not good up in the mountains. Okay, very good. We'll stop here.